Great load balancing and decreasing performance. If the value of E is very high, we just keep applying the algorithm even though the critical value has already been achieved. This leads to lots of time and over-division. Over-division leads to great overhead decreasing performance. Of course, the best value leads to the best division, like that example there, and best performance. So we have already divided the tiles. Now, how to distribute them? We know that distribute any tiles among R rendering nodes in order to have each rendering node with the smallest cost possible. It's an NP complete problem. So we solved it first applied in the data mining field. And it states that we can have a reasonable number of tiles with small standard deviation by finding a critical value of W. So I will explain this algorithm by means of an example. First, we need to gather some parameters from the tree. The first one, of course, it's the W parameter. That is initially the average cost of all the leaf nodes. Here we have 10 nodes, total cost of the tree 100, total cost of the leaf nodes 100, so W equal 10. The second one, it's the delta G parameter. That is the difference of the tallest leaf node in the tree and the shortest leaf node in the tree. So in this case, that's why we have W plus 1 possible values for cost and delta G plus 1 possible values for area. So the width of each of those intervals is the total width of the cost we can have, delta D, divided by the possible width, delta D, W plus 1 times delta G plus 1. So we know that this width that we call delta D is given by this formula. So it's mathematically proven in the previous work that whenever this delta D changes order of magnitude, the critical value has been achieved and we do have the best division. So what's the change order of magnitude? Well, in this work we simply state that if a value of delta D of the current iteration is p times value of delta D of previous iteration, order of magnitude has changed.